All right, how's everyone today? We're going to do limiting reagent and percent yields. Okay, we'll talk about it for a little bit, make it, try to make sense out of it. Okay, clear? Are we all right with that? Okay, now, let's take a very simple equation, and what's the first thing you're going to do? Try to get used to it as almost like an arc reflex. What are you going to do? What are you going to do to it? Yes, Simon.
Like the mass?
Yeah, the masses, the stoichiometric masses that are just as it's written. Okay, so it would be what? How many grams of that? 2 moles of H2 would be
4 grams.
4 grams, 32 grams, and 36 grams. Correct? Now, let's take, let me show you what limiting reagent is. Let me just show you. Let's say, for instance, and you could do this by inspection. You know, you could. The problem could be very easy. It might be a little bit more difficult, but either way, limiting reagent is not difficult. It's just doing 1 or 2 mass-mass relationships. That's all it is. Let's say I have 100 grams of each. Can you see by that 100 grams each, which one is going to limit the reaction? Which one's going to be in excess and which one's going to limit the reaction? In other words, if I increased what mass, hydrogen or oxygen, would I increase the amount of water produced? Okay, so think of it this way. If you have 4 grams of hydrogen, you're going to need how many grams of water?
32.
32. So you're going to need 8 times the amount of, I'm sorry, what did I say? Did I say that right? If you have 4 grams of hydrogen, how many grams of oxygen are you going to need? 32 grams, right? Did I say water? I might have, whatever. All right, so do you see that you're going to need 8 times as much oxygen as hydrogen, correct? Right, now. So if I use all 100 of the hydrogen, how much oxygen am I going to need? 800, right? So do I have 800?
Nope.
So what's going to limit the reaction? What's going to limit it?
The hydrogen. I mean the oxygen.
You have two types of reactants. You have limiting and excess. You have limiting and excess, right? So you can see by inspection that is the limiting reagent going to be oxygen or is it going to be hydrogen?
Oxygen.
Yeah. Well, let's see. If I use all of this, how much of this will I need? Okay? If I use all of this, how much of this will I need? So, if I say oxygen to hydrogen, that's going to equal 32 to 4. That'll equal 100 to x. So what's x going to be?
12.5.
12.5. So I'm going to need 12.5 of this. So therefore, what's going to be limiting and what's going to be excess? Oxygen's going to be limiting, right? And hydrogen's going to be excess. Well, there's this very simple way of doing it, to be sure. Some of you are a little unsure right now. You're kind of mumbling to yourself, thinking that you might be right or whatever. But there's another way of doing it. Why don't we do, there's only 2 problems you can do. What's x going to equal? What's x going to equal? 800. Do I have 800?
Nope.
No. So what's going to be limiting?
Oxygen.
The one that you don't have enough of if you burn the other one. Right? So limiting is going to be O2, and excess is going to be H2. Clear? Easy? So far so good? I mean, fairly straightforward. I'll give you one that's a little bit more difficult to see. All right? I'll give you another problem. But let's use this problem for a moment. Okay. So we know that this is going to be limited by the amount of oxygen, correct? Right? Now, if I burn 100 grams of oxygen with excess hydrogen, how much water will I get? How much water will I get? Can you do that? Can you try that yourself? Right now? Can you try that yourself? Set it up anyway. I'll set it up on the board. You set it up on your paper. Usaba, you want to put the phone away? Thank you very much. Wonderful person. No? So we know that this is going to limit it, so we have to use this, correct? We know we're only going to use 12.5 of this. So we're going to use this. So O2, 2H2O. What's the constant ratio? What's the constant ratio?
1 to 8.
What is it?
1 to 8.
No.
8 to 9.
Isn't it 32 to 36? Isn't that the constant ratio? Isn't it? Aren't you comparing oxygen with water?
Yeah.
So isn't the constant ratio oxygen to water? Yes? So what would be, if you're going to, how much oxygen are you going to burn? 100, right? How much water will you get? You can do it. You can do it. Great faith in you. 36 times 100 divided by 32.
112.5.
What is it?
112.5.
112.5 grams. Okay, now, listen carefully. If I consume the limiting reagent, how much water will be produced? 112.5 grams, correct? That's the theoretical yield. That's called the theoretical yield. Theoretically, that's what I should get. I shouldn't get more than that, I shouldn't get less than that. So we call that the theoretical yield. Is that spelled correctly? How do you spell yield? Look it up.
Y-I-E-L-D.
So it's a theoretical yield, right? Right? Are all experiments perfectly performed? Do you think I'm going to get 112? No. I'm going to have error, right? Let's say I get 105.
Some evaporated.
So evaporated. The procedure that was used was not very good. The glassware didn't seal, whatever. System error, systematic error, unavoidable.
Are there perfect ways to get the theoretical yield?
There's two words that are mutually exclusive in this world: science and perfect. You can't use them both in the same planet. Perfect and science. Can't do it. Okay? The thing I like about science is it's really, really, really okay to be dead wrong. Absolutely wrong. Okay? So, let's say I get 105 grams. Is that what I said? That's actually what I get. What's that called? That's called the actual That's the actual yield, 105 grams. What would be the percent yield? Obviously, it would be what?
Percent error?
No, not the percent error, the percent yield. What's the percent yield? What do you think? Wouldn't it be what? What would the percent yield be? It's the actual over
93%.
so what's 105 over 112.5?
93%.
93%. Good. So 93% yield. Not bad. Pretty good. That's it. Shall we do a little bit? We'll do a problem that's a little bit dicey looking. Okay? We'll do a problem that's a little bit dicey looking. Okay. Okay. We're going to do this one. We're going to do a few things with this particular problem. Okay? We're going to do a few things. All right? Let's say let's say I have lead 2 nitrate and I combine it with sodium iodide. And right now, right away, this is lead 2 nitrate. Right away, I want you to start doing the atomic weights of these particles. Okay, right away. And then you're going to get lead 2 iodide plus this is going to be a solid. We'll put an arrow there. This will be AQ. This will be AQ. Okay. And how do I balance that?
Putting a 2 in front of the sodium iodide.
Okay. We're scrunching here. No scrunching allowed. So let's say 2 sodium iodide.
And 2 sodium nitrate.
2 here.
Yeah.
Okay. So what? What are we doing?
We balanced it.
Did you balance it? Okay. What are the masses up top? I want to say, what are the masses? I want you to do the mass here. What's 1 mole of lead nitrate? So what's the mass? What's the atomic weight of lead? Simon? $207. Good. Just use mass numbers. It's easier. You all right with that, Simon? You sure? Are you awake today? Okay. So 207. All right. So what's that? 14 plus 3 times 16, 48. What's 14 plus 48? 62 times 2. 124. So 124 plus 207. 331. Okay, what about 23 and what is iodine? What is it? 127. So 23 and 127 is? What is it? Simon, are you okay today? 150, good, times 2. 300. And what about 207 plus 127 plus 127? So put that in your calculator. 207 plus 127 plus 127. What do you got?
461.
What is it?
461.
461. And then what is 23? Put in your calculator. 23, 14, 48. 23, 14, 48. What do we got?
85.
85, are you sure?
Yeah.
You're positive. 85?
Yeah.
And what's 85 times 2?
170.
170? All right. Now let's see if we're right. What's 170 plus 461?
631.
631. And by inspection, I hope it's by inspection, 300 plus 331 is what?
631.
So we're right. We hope. Unless we made more than one mistake, right? Okay? Yeah. I'm like looking at Simon and thinking that's a distinct possibility today. Okay. So let's say I have 64 grams and 60 grams. Pretty close, right? Difficult to do by inspection, isn't it? So which one is going to be limiting? Which one's going to be limiting? Difficult to do by inspection. So what's the foolproof way? What's the foolproof way? Do two problems, right? You ready? You ready? Okay, so you have lead nitrate over 2 sodium iodide equals 331 over 300 equals 64 over x. What do you got? What's x?
331.
So what is 64 times 300 divided by 331?
58. That is 58.
What is it?
58.
Just 58.
58.0006.
So we could reasonably say it's 58. All right, so 58. So if I burn 64, I have 58. Do I have 58? Do I?
Yeah.
I do. Right? So what's going to be limiting?
The lead nitrate.
That's going to be limiting?
Yeah.
Really? How is that limiting?
Because we have.
I have
access
plenty of
to
that.
Yeah.
But all right, you think that's limiting? I have plenty of that, right? I have plenty of that, correct? All right, so now let's do this one. Let's do 331 over 300 equals x over 60, right? Equals x over 60. So what is 331 times 60 divided by 300? I'm going to circle the answer to the problem.
66.2.
Do I have 66.2? No. So what's limiting? What's limiting?
Lead nitrate.
Was Ishmael right? Absolutely. It's a dead giveaway. You really only have to do it once. Because if you do this and you have excess, you're cool. You're golden. If you do this one and you don't have enough, you're still golden. Right? So if you do this one and you have enough, that's excess, that's limiting. If you do this one and you don't have enough, that's limiting, that's excess. You get it? You all right with that? Okay. I'm going to turn this off. I think we're pretty good with limiting. Do you think you're good or no? And then I'm going to come back and I'm going to do another kind of problem. Okay? You all right with that? All right. Kind of using this. So we'll call this, I don't know, stoichiometry part 6. Okay? Yes?